Well, hello there. So let's talk about capacitors. That's our topic for this week, capacitors and inductors. So we're starting with capacitors. Capacitors are a energy storage element. So they're passive. They don't generate electricity or generate power, but they can store it, unlike something like a resistor. The physics of it we don't get into in a lot of detail in this class, but basically if you have two plates next to each other, with something that's not conductive in between. If you apply a voltage to that plate, then charge piles up on each plate. So you get a bunch of plus charges piling up here and a bunch of minus charges piling up there. So the charge, it's C, which is the capacitance of, which is due to the geometry and the materials and the dielectric and everything here, times the voltage. That's how much charge we get. And so what you see is if you change the voltage, if we change V here, then it will reach a different equilibrium of charge. So the battery's pushing charge out here, they pile up here, but they repel each other, so at some point they reach an equilibrium. And if you change the voltage, you change the charge, which means current flows. These electrons go back in or out of the voltage. So changing voltage gives you current. That's the big takeaway here. These are the equations that we will use through the whole class here. These two down here, I and V, we're interested in. We don't care so much about charge, although it is deep in the physics there. So here, current, the current through the capacitor is the capacitance times dV dt. So here, changing the voltage, like we just said, gives you a current. This is like Ohm's law, except it's a differential equation. So when we have been analyzing resistor circuits so far, we've been using Ohm's law and Kirchhoff's laws to do our node and mesh analysis. So we can do the same thing, we just have to put this where it's integral form. Here's where we're solving for V by integrating both sides. So 1 over C integral of I dt plus an initial voltage, initial condition that we need at time t0. So we have these two forms of Ohm's law for capacitors. It's just the differential equation for capacitors. And we can use these just the same way. It makes the math really complicated, but the solution process, the circuits, is really the same. So that's how we're going to go forward. So in steady state, the derivative goes to 0, which means the current goes to 0 in steady state. So in DC conditions, when we're totally charged, the capacitor looks like an open circuit because open circuits have 0 current. Because of this equation, the voltage has to be continuous. We can't have instantaneous changes, which would give infinite dV dt terms. So we can't have infinities, that would be infinite amps there. So no sharp changes in the voltage. And capacitance is measured in farads, F. This number was chosen historically, and 1 farad is huge. If you see a 1 farad capacitor, be careful. It stores a lot of energy. Could be dangerous to handle. Microfarads, millionths of a farad, are much more common. So again, we don't really get into the physics or the construction of capacitors, but there's some good images and descriptions in the book, so I will let you read them. But basically, we're getting metal conductive things separated by non-conductive things. So mica and metal foil, and you can roll these up. Sometimes there's a dielectric inside. A lot of different kinds of capacitors that you might find as well. But for us, they're all ideal capacitors, and we'll just treat them with the same equations. So we have this equation for I and V with the capacitor, so we can calculate the energy and the power. So power is voltage times current. So if we use the equation that I is C dV dt, then we have C dV dt, that's our I, and then multiply it by another V, and that gives us an equation for power in terms of the voltage across the capacitor. And if we integrate power over time, we can find the energy stored in the capacitor. This starts at negative infinity because that's the proper way to do this, changing the voltage history over time, changes the energy stored. But in the end, the current voltage, that right now voltage of the capacitor, is what tells you how much energy is stored inside of it. So using that differential equation, C dV dt is the one that rhymes, and that's the current through the capacitor. That's how I remember it. If we're given voltage as a function of time, so these are straight lines, we can write functions for those, and we could take the derivative of the voltage, which would be the slope. So we'd be graphing the slope of each section here. So here we have a positive slope. This is current versus time, voltage versus time. So the voltage is increasing linearly, so a constant current. The voltage is flat here. Current is 0. Voltage decreasing, negative slope means negative current. And the voltage is flat again, which means 0 current. If we went the other way, if we started with current, then we would integrate. So if you integrate the area under this curve, you can see we start with no area. As we move along in time, the area will be increasing linearly as we add each little rectangle. That's where we get the voltage. Here we're not changing the area, so the voltage is going to stay constant. Here we're adding negative area as we move along in time between 4 and 5, so the voltage has to decrease. So the integral of current gives us voltage with a 1 over C factor in there. And power and energy, we're using these same equations. Voltage times current for power, and energy is just voltage squared. So with those differential equations for how a capacitor works, we can use Kirchhoff's current law and the differential integral equations and make some new interesting discoveries. So here's one where we're looking at capacitors in series with each other. So we have 3 capacitors in series, they're head to tail. There's only one way for the electrons to go. And we know that because they're in series, they have the same current. IS goes through each of these. And so IS is here, and I is C dV dt. They each have a different voltage across them, so C1 dV1 dt, C2 dV2 dt, C3 dV3 dt. Those are all equal to each other, same current. If we do Kirchhoff's voltage law going around, then we find that the voltage at the source equals V1 plus V2 plus V3 minus Vs plus V1 plus V2 plus V3 equals 0 going around. And we can combine these together. If we take the derivative of this equation, then dVs dt is dV1 dt plus dV2 dt plus dV3 dt. So here, with an equivalent capacitor on this circuit, we would have this equation. We can put dV1, dV2, dV3 in for this, which comes from the voltage, from Kirchhoff's voltage law. And then seeing these up here, we can solve for the derivatives is IS over the individual capacitor. And that's what we're getting here. And if we simplify, we can find that the equivalent capacitance is 1 over the 1 overs. So it's just like the opposite of resistors. So in resistors series they add, and parallel is 1 over the 1 overs. In capacitors, series uses the 1 over the 1 over equation for the equivalence. We do a similar analysis with parallel capacitors. Here we can use Kirchhoff's current law, and because they're in parallel, the voltage is the same across each one. So here's Kirchhoff's current law, and we use the same voltage when we go into this differential equation form of the current, C1 dV dt, and this would have to equal C equivalent dV dt, and so if we factor out the derivative of the voltage, we get C equivalent equals the sum. So capacitors work the opposite of resistors when we're doing series in parallel. So in parallel, capacitors add. In series, it's the 1 over the 1 overs. Okay, so looking at this, the DC steady state, DC direct current, steady state means a lot of the times you'll hear after a long time. So we apply a voltage to this circuit, and the capacitors charge, and after a long time they're charged and nothing really changes. Everything goes to a flat line, as we'll see when we do the function as a function of time soon. But for now they get charged and everything becomes kind of static, and that's our DC steady state. And so our derivatives have gone to 0 because it's not changing anymore. So here's the derivative. So dV dt has to go to 0, which means current goes to 0. So at DC steady state, no current is flowing. So if there's no current flowing, it acts like an open circuit. So we can analyze really complicated circuits with capacitors, and very soon with capacitors and inductors, that would normally lead to complicated differential equations, systems of differential equations to solve. But pay attention to the problem, because if it says DC steady state, we take the capacitors and just replace them with open circuits. So we cut them out. And now we're back to a circuit that has sources and resistors, and we know how to analyze that. We can use node and mesh analysis, and we don't have to use any differential equations or anything. It's just got a nice algebraic solution. So here is some analysis of this circuit. One thing to notice, when we have open circuits like this, just like we see in Thevenin analysis sometimes, we get a dangling resistor, this 40 kilo ohm resistor. So no current can flow through that. So when you do your node and mesh analysis, this 40 kilo ohm resistor is not having any effect. So if we do it's node analysis solving for this voltage V, V minus 20 divided by the 20 kilo ohm resistor plus V divided by these two resistors in series, 30 plus 50 kilo ohms, and we can solve for V. That gives us V1 because it's directly connected to V, and the ground node is 16 volts. The V2 here is between this node that's between 50 and 30 and this side of the 40 kilo ohm. But because there's no current through here, the 40 kilo ohm, there's not going to be any voltage across this resistor. So this side is ground. So we can use the voltage divider with V up here and ground on this side to find the voltage at this node, and that's our V2 node. So 10 volts there. So we can solve for the capacitor voltages, we can solve for everything without having to do any differential equations. Okay, well, that's it for now. So I will see you in the next video where we will go through the same process, the differential equation instead of Ohm's law, series, parallel, some basic calculations for inductors. So I'll see you in the next video.